G'day guys, Mr. Bennett here. Today we're going to be looking at how PET scanners actually work, and that's actually stands for positron emission tomography. Alright, so I've got a quick video to show you and then we'll talk about how that works in a bit of more detail.
Scan creates 3D images of the body. It does this by using radioactive tracers, which are usually administered to a patient through intravenous injection. The tracers are made up of carrier molecules that are tightly bonded to a radioactive atom called an isotope. The carrier molecule can interact with or bind to specific proteins or sugars in the body. The carrier molecule that will be used depends on what the doctor is looking for. If she suspects cancer or is monitoring a known cancer's growth, she may use FDG, a modified form of glucose, which gets absorbed by tissues. When tissues absorb a lot of glucose, it may indicate a cancerous tumor. The radiation from the tracers poses little danger to the patient since they quickly pass out of the body. The isotope produces small particles called positrons, which interact with surrounding electrons. This interaction results in the complete annihilation of both particles, releasing two photons that speed off in opposite directions. The detectors in the PET scanner measure these photons and use this information to create an image of the distribution of FDG in the body.
So if we're looking at that, I think it gives a very good, good starting point to understand this. So just talking about the different parts. Now, this particular one is an example of one of the isotopes: 2-fluoro, 2-deoxy, D-glucose, FDG. That's the one she talked about. So if the doctor suspected that you had cancer, then they would basically inject you with this isotope, and the key ingredient is fluorine 18. Okay, that's the particular isotope that's going to decay and give us the information. So the 2 just relates to which carbon it's bonded to in that chain. So there are a series of radioisotopes that they might use. So depending on what they were looking for. So here's just a list of 4 of them. So we've got carbon 11, oxygen 15, fluorine 18, or bromine 75. Now you notice the half-life of these particular isotopes is quite short. So a couple of things that might happen is they would probably produce these isotopes in a laboratory at the hospital using a cyclotron. And so then they could inject it into the patient. So obviously you inject it in the patient and then you want to do your PET scan quite quickly after that. Alright, so that's the process there. Now, just going to go down to looking at how that actually works. Right, so I'm looking at a tomography, positron. So what actually happens is we get our positron by using a process called beta positive decay. So that's what actually happens. That radioisotope undergoes beta positive decay, produces a positron. The positron will hit electrons that are inside the tissue. So when it does that, it will actually cause an annihilation, and so therefore for us to have conservation of energy, it must produce 2 gamma rays going in either direction, 180 degrees from each other. Alright? Now the key concept is that if you inject this isotope, which is basically glucose, into the body, we know that cancer cells are quite aggressive in the way they grow, but also they consume lots of blood and they consume lots of energy. So they are going to produce, or they're going to consume more of that glucose than other cells in the body. So let's say you've got a tumour in your brain, and what's going to happen is you'll see lots more of these positron emissions occurring from a part which is basically attracting more of the glucose, and so therefore that gives you an idea where the cancer might be. Now, the way this detector works, a gamma detector, is a big like donut, and so therefore let's say you've got this one going this way, you've got a emission from there, a gamma ray going there, you're going to have the detector detects whether there's one going in the opposite direction. Does that make sense? If it doesn't detect that, then it won't actually pick that gamma ray up. It actually won't record that in terms of the visual diagram you saw, which produced a 3D diagram. So we're looking for a gamma ray going that way. We're looking for the paired gamma ray going the other way, and obviously the time difference between that gamma ray and that gamma ray will give you the distance from each of the points where it actually hits. Get the idea? So because we know that these things travel at the speed of light, so therefore the short distance time difference between those will give you not only where it is along that line, but what distance along that line is. Does that make sense? So that's how the detector works, and it produces 3D images. Now the new thing with PET scanners is they use them with other things like MRIs or CAT scans and so on. They found that's actually a better way of looking at the information there. Alright, so the 3D image of that is actually quite amazing in terms of when you start looking at how the detector works. And that's certainly been a really, really positive source of detecting cancer in humans. And so, you know, I would think a device like this has saved certainly a huge number of lives over a long period of time, over a fairly short period of time. But what it does mean for the doctor is the doctor can operate and knows exactly where the tumour is and how big the tumour is. So therefore they can make a better diagnosis of the issue that the patient might be under duress with. Alright, so again, you know, this is certainly a great invention and a great use of radioactive decay. So this is the application of radioactive decay with that. Obviously the other application of radioactive decay is carbon dating. So when you do carbon dating, you would do that for things like anything that was organic, had carbon in it when it was alive, so any plant or animal. So you use carbon, but if it's not, you know, they also do radioactive dating on rocks and that sort of stuff. And generally when they're doing that, they'll use the amount of uranium that's actually in the rock. Uranium and lead, right? So obviously when uranium decays to lead, and so therefore looking at the ratio of those two elements in most minerals, right? So there's lots of different ways of doing the radioactive decay dating, right? So you're looking at different elements, different isotopes, and how they actually decay back to other forms, right? So this one here, quite often you'll get a question in the exam talking about this process and what actually happens, but keep it simple. Right, it's basically a beta plus decay where you produce a positron. The positron's going to interact with or collide with an electron. When it does that, it actually annihilates it and produces two gamma rays that travel at 980 degrees to each other, and the detector picks those two things up. Right, if you've got any questions about this, please make sure you catch up with me in class and we'll go through it.